All right, let's play. Given a state space system, find the transfer function. Let's go ahead and do some labeling here just to make this easy on ourselves. State space, remember, is x dot equal to ax plus bu, y equal to cx plus du. A is right there, B is right there, C is right there, and we don't have D. So, gone. This is the standard form, that's what we've got. We know how to map it, so let's get to work. The transfer function, h of s, is going to be equal to, remember, the output over the input is equal to y of s over r of s is equal to, here we go, c times si minus a inverse times b plus d. We don't have a D matrix in our system, so that's gone. And let's just fill this out like we would. In regular algebra problems, C is 1, 1. Si minus A, I'm going to call M. And B is 2 and 2. So to go from state space to transfer function, you're using this formula. Yeah, there would be a plus D right here. That's the standard form formula. And the real meat and potatoes of it is right in here, this Si minus A inverse, which I'm calling M. So let's deal with M. Let's deal with M in green real quick. M is equal to Si minus A, which is equal to SS0, 0 minus A, 2, 0, 0, 3. Okay. S minus 2 is S minus 2. 0 minus 0 is 0. 0 minus 0 is 0. And S minus 3 is S minus 3. There's M. Now we need to solve for M inverse. Standard formula for the inverse of a matrix is 1 over the determinant of that matrix times the adjunct of M. The adjunct of M on your 2 by 2 is where you're taking your diagonal entries, flipping them, and then changing the positive or negative signs of your off diagonal entries. Here they're both 0, so we're not going to do anything to them. So let's go here. We have two things. We need a determinant of M, and we need an adjunct of M. So let's solve for the determinant of M. Let's do it right here. The determinant of M is equal to little a times little d minus little b times little c. What do I mean by that? I mean that for any matrix, A, any, is going to be A, B, C, D. So your determinant is those ones multiplied together minus those ones. So A and D here, S minus 2, S minus 3. So we have S minus 2, S minus 3, minus 0 times 0, which is a 0, so nothing there. The determinant right here. So 1 over the determinant times the adjunct matrix here. We're going to switch the diagonal entry, so it's going to be S minus 3, 0, 0, S minus 2. And then we're dividing everything by the determinant, which was S minus 2, S minus 3. Okay. We have M inverse, and that's going to take care of this whole thing right here. So let's rewrite. Over here we have h of s is equal to y of s over r of s, which is going to be equal to c 1 by 1, or not 1 by 1, 1 and 1, m inverse, which was s minus 3, 0, 0, s minus 2, all divided by s minus 3, s minus 2, times b, which was 2 and 2. Okay. When we're doing this formula, you'd think, oh, you could just cancel these out. Cancel the s minus 3s, and now you're just left with 1 over s minus 2. Yeah, you can do that. Don't. Transfer function, you don't want to lose states. So let's just keep it the way it is. So let's do this section first. Right here. That's going to be a 2 by 2 times a 2 by 1, leaving us with a 2 by 1. We're going to have s minus 3 times 2. So 2 times s minus 3 times 0 and 2. Followed by 0 times 2 is 0. 2 times s minus 2. And this whole thing divided by s minus 3, s minus 2. And we're going to multiply that by our c, which was 1 and 1. So let's go ahead and do that out. We're going to have a 1 by 2 times a 2 by 2. It's going to leave us, as I was, with a 2 by 1. It's going to leave us with a 1 by 1. 1 times 2s plus 3 is s minus 3, s minus 3 plus 2s minus 2 divided by s minus 3, s minus 2. Now, just for clear presentation here, when I divide under the matrix, the whole matrix, that's saying element-wise division of each thing. When I do inside of the matrix, this is just one element, because this is just a 1 by 1. So this is just this over that. But we got to clean that up. That's going to be 2 times s minus 3 plus s minus 2 divided by s minus 3, s minus 2. And here's your transfer function.